Okay, yeah, then thank you for the brief introduction. My name is Billy Naumann. I'm a PhD student at the Technical University or the University of Technology in Chemnitz, to be precise, at the Operating Systems Group. And well, we did a formal analysis of the timeliness property in the REST protocol. Um, oops. Before I start my talk, or I want to start my talk with a short quote by Sir Tony Hoare, who once said that the job of formal methods is to elucidate the assumptions upon which formal correctness depends. And well, in the end of the talk, we will see why this is a quite fitting quote right here. The WASTA protocol is a protocol that's used in the railway industry, and well, the railway industry is, for hopefully obvious reasons, a safety critical area. Therefore, the correctness of an end-to-end communication has to be ensured. You can expect that we have a short introduction of this protocol, and as I said, we will do a formal analysis of the timeliness property right here. Well, let's dive right in. Let's take a look at the Rail-Safe Transport Application Protocol. That's what WASTA stands for. As I said, it's used in railway signaling and especially in the in the communication, for example, with trains or with signals on in the field. For example, trains can be notified about current speed limits on the track. And I think that's also a point where you can see why it is really crucial that correctness here is guaranteed. Because if a train, for example, isn't notified or is notified too late about a speed limit, well, let's say unpleasant things can happen, and well, that has to be avoided. This protocol introduces two layers above the transport layer. The first one, which is indeed a little bit out of scope for today, is the so-called redundancy layer, which introduces just a redundancy in the communication by using multiple transport channels. We want to focus on the so-called retransmission layer, which, as the name suggests, handles any communication errors or failures, and therefore enables a retransmission of any lost message right here. On the right-hand side, here we can also see a portion of the state graph, basically of that retransmission layer. The upper part is mainly for the connection establishment, so that's not too much into scope for today. We want to focus on the lower part, where we can also see that, well, this layer, also, as the name suggests, enables a retransmission. Usually, we are in the up state right here, and as soon as a message got lost, and that is not notified, that is noticed by a communication partner, that communication partner will issue a retry request, which in turn already is part of a handshake that will end up with the retransmission of the lost messages. Well, as you can see, that's also a point where the timeliness becomes an important factor, because if we don't really know how long the communication takes and how many tries basically we have to do, that, let's say, isn't trivial to just state that a message can be on time in all cases. To deal with timeliness, the communication is organized in so-called message round trips. We will see why this is the case in just a minute. These round trips basically are formed by so-called heartbeat messages, which are sent by a communication partner every THB. And also, each communication partner has a so-called round trip deadline, TDL, until which the round trip has to be finished in the end. Well, and our main question was to well, analyze this protocol and see if it indeed achieves timeliness. To do so, let's take a look into the round trips themselves. Here you can, or before we can do that, we just should talk about the properties of the nodes or the communication partners, because by the standard, they are, or by the standard that forms this protocol, they are assumed to have correct clocks. That means basically they can be unsynchronized, but the important factor is that they have a limited drift right here. So these clocks can have, as I said, unsynchronized values, but they can only be a little bit faster or a little bit slower than the real time, so to speak. Also, all messages that are communicated have so-called sequence numbers, which for us right now are only important for the detection of a lost message. So if a message arrives at a communication partner that has not the expected sequence number, we can assume that a message in the meantime has got lost. Also, and that's the more important part, these messages feature timestamps. Basically, as soon as a message is sent, the current timestamp of the sender of that message is copied into the message and, well, transmitted to the receiver of the message. These timestamps, however, are not interpreted as, on the receiver side. As I said, the clocks aren't synchronized, and therefore the receiver shouldn't make the guess that, okay, in this message, the timestamp seems to be okay for me, whatever that means in the end. And therefore the message is in time. That shouldn't take place. Yeah, the receiver cannot determine the timeliness just by the message. What is done instead is that a reference time point called T, in my case here, is determined on the receiver side prior to the message that is to be which timeliness is to be determined. And well, this timestamp basically is sent to the sender of that message, which later on answers to that message with a so-called confirmed timestamp, or with another message that's carrying a so-called confirmed timestamp. Well, this confirmed timestamp is nothing else than just exactly that timestamp of the original receiver in the first place, which is just copied over. So you can see right here that value T is exactly the value where the receiver has, well, which the receiver has chosen as the reference point. At that point, basically, the receiver starts a timer corrected by the delay between the original time point T and the moment where he received that message, which corresponds to the remaining time until that round trip has to be finished. Later on, the receiver sends, maybe with the next heartbeat, another message carrying a greater timestamp, indicated as timestamp is greater than T right here, which in turn is then answered by the original sender with the message that determines basically the timeliness. If that message arrives prior to the deadline, everything is fine. If not, well, the timeliness is violated in this case right here. Okay, up until now, we have seen a perfectly fine communication without any errors. Let's tackle this problem and see how the error model is specified at this point. The standard for this protocol states that during a round trip, at most one message can be lost from one of the communication partners. I said the standard states this. Actually, this is already a little bit imprecise because the standard doesn't formulate this error model exactly like this. It's more or less just implied because they give a few examples about the error situation, but they don't really say what they assume about the error behavior. But that's basically condensed from these examples, what they are assuming. The problem at that point is that this is a little bit unrealistic, to be honest, because there is not really a relation between these both communications channels between sender and receiver, and basically the other channel between receiver and sender. So as I said, that's a little bit unrealistic, but as I said, as that is the error model that's used in the specification, we decided to stick with that and, well, used it for our analysis too. This in turn implies fault-free retransmissions. Well, if only one message can be lost, then that has to be the message that will be retransmitted in turn. And therefore, during retransmissions, no additional messages can be lost anymore. The standard defines a guarantee, or it claims a guarantee for a deadline bound, which is shown in this box right here. They say if the value for the deadline is at least 2 times the worst case communication delays between both sender and receiver. So time from receiver to sender and worst case time from sender to receiver, plus 3 times the worst case time between 2 consecutive messages. That's the important part of the communication partner. So we don't take they don't take the communication or the heartbeat time of the own instance basically into account, but just the heartbeat time of the communication partner. I already made that a little bit orange, so you can assume that we have found something right here, but we will come back to that later. Before we can do that, as we have seen, we have already some minor assumptions basically for the error model. We have a few things more that aren't really as clear in the standard as one would like. For example, in the specification, or at least that's more or less a part that we have to assume, the violation of the message sequence is handled solely by the retransmission layer. Basically, the redundancy layer, which is, as I said earlier, out of scope for today, is already capable of reordering messages. For example, if on one of these redundant channels a message arrived a little bit earlier. But for us, right now, we just decided that everything basically happens on the retransmission layer. Another aspect that's a little bit unclear is how the responses in the retransmission handshake and basically also the retransmitted messages are handled. We decided that these responses take place immediately, so there is no delay between, for example, 2 consecutive messages. They are all sent at the very same moment in time. On the other hand, we have some assumptions and our approach how to model all of this. As we already have seen, we've chosen for the timestamps to be expressed as relations. So we said our timestamp is equal to t or greater than t, for example, rather than using explicit values, which would be the case in a real execution of this protocol. This is mainly to encounter or to deal with the problem of state space explosion, which basically would mean that which basically means that we have reduced the all possible behaviors with different timestamps to, well, basically the same behavior, just with these relations. Also, we have to assume that the message sequence violation is indicated by the channel. That's a little bit tricky, I guess, but the thing is right here, all on the other hand side, that would be done by the redundancy layer in the end. But as I said, that's out of scope. We had the channel basically to indicate that a message got lost. We will see that in a second when we look at the model for the channel. Also, as we said, okay, we have all the handshakes and the retransmission of messages at the same time. And by the second basically assumption, or by the result of the error model, that no message can get lost during the retransmission, we have condensed all the retransmission part into a single response message. As a last assumption, we have looked at this as from an asymmetrical point of view. So we don't have a, let's say, symmetrical execution of this protocol, but just a round trip started by the receiver and, well, also basically also ended by the receiver in the end. We will look at the specific modeling right now, which should make that a little bit clearer. Well, we modeled it as a decomposition of the retransmission layer, pretty straightforward into sender and receiver. And we introduced a additional model for the channel as the underlying transmission infrastructure, basically. We used timed automata to model all of that. And as I said, we also did this only for a single round trip because the behavior of this round trip is basically invariant for all the round trips that are occurring. Yeah, the graphic down here pretty much shows everything once again. The receiver starts the round trip by setting that reference time point T, and is also responsible for determining the timeliness in the end as soon as he received basically the final message of that round trip. The sender, on the other hand, just has to respond to the received messages in the end. And in the middle of the channel, as I said, it's a FIFO channel. It's a time channel such that we have information about the worst case transmission times. And as it has to implement the error model, it's a unreliable channel. As I said, it can only lose one message right here. So the term unreliable is a little bit strong, maybe. But as I said, that's the error model. Also, it has to notify about the lost messages. We choose the tool UPAL to do the, which is capable of symbolic model checking of networks of timed automata, which basically fits perfectly into how we wanted to model, well, this system. The composed system in UPAL is analyzable via so-called timed computational tree logic. For us, we were able to express or assert that no deadline violations occur by a safety formula, which is shown here, which basically states that for all execution paths in each state, if that state is the end state of such a round trip, it has to hold that the time of the receiver has to be less or equal than the deadline for the timeliness to be ensured. On the right-hand side here, you can see our model of the channel, which is, as I said, basically a pretty straightforward model. As I'm already a little bit late in time, I'm going to go only briefly over this. As you can see, we have just two states. The channel is idle. In that state, no time is advancing, which is made sure by that state invariant here. And as soon as a message is passed to that channel, this upper transition here is taken, and the channel moves into the transmitting state, where he can reside until, or at most until, the worst case transfer delay is reached. At that point here, it can choose if non-deterministically if he wants to transfer that message to the receiver, or for one time only if he loses that message. Yeah, and in both cases we end up in the idle state again. So much for the channel. I also want to take a brief look into the receiver model, which is a little bit, well, bigger than the channel, but still, I hope at least I can make clear what is happening here. The important states are basically the start state right here, the waiting state right here, and in the end, the end state right here, because these are these three states which are, well, which represent the round trip in the end. We start in this well, start channel by sending the first message and setting that reference time point T, and transition into the waiting channel. Here, we are waiting for a response to that message. And if that response occurs, we would take this edge and right here, under the assumption that everything went well and we did not lose a message, and that message is indeed such a heartbeat or data message, we would check what the confirmed timestamp value would be if by transitioning into this state right here. If that indeed is a value that is not greater than T, so T itself, once again, then we would transition back to the waiting channel, state. On the other hand, if it is indeed a message carrying a confirmed timestamp that is greater than our reference point, then we would transition into the end channel and, well, basically are done with this round trip. All the other states that you can see are used to handle retransmission right here. So as I said, as I'm already a little bit late on time. So I do think that's everything I want to say for the receiver model right here. As I already said earlier on, we were able to, or basically not we, but Rupal was able to find a counterexample where this deadline is indeed violated in such a situation. And as I said, that already leads to the point where the claimed guarantee by the standard is indeed invalidated. We were in turn able to analyze this situation a little bit further. And well, the problem with that bound, as I said earlier on, is that it only considers the communication partner's heartbeat time. As you can see here, these are basically two key situations where the important information of a timestamp that is greater than our reference point, or the confirmed timestamp that is greater than our reference point, which both are necessary for the round trip to be completed, are shown. As you can see, the first case where the timestamp itself got lost is basically the problem of the receiver, because that receiver has to retransmit that message again. And on the other hand side, the confirmed message is the problem of the sender, which means that the sender has then in turn to retransmit this message again. Yeah, we were able to analyze the situation and provide or suggest a better deadline bound, an improved deadline bound, which also takes into account the worst case transmission delay times as before, but now takes into account the maximum of the heartbeat time, or the maximum of 2 times the heartbeat time of the receiver plus the heartbeat time of the sender, or 2 times the heartbeat time of the sender plus that of the receiver. Okay, basically that's what I wanted to show. Let's conclude. As we have seen with the introduction, or with the quote in the introduction, the use of this formal method, especially the use of Rupal, showed, or by the use of that, we were able to show ambiguities in the protocol specification and also find an error in the proposed bound. Yeah, and therefore, basically exactly what this quote wants to try to tell us is once again shown right here. Also, we were able to provide a suggestion for an improved bound, which as future work is basically part of the generalization of that bound in collaboration with the protocol committee, and an expansion to other protocol aspects, especially to take into account the redundancy layer, which was out of scope for today. Okay, that's basically my talk. I want to thank you for your attention, and well, I'm open to your questions.
Okay, thank you very much, Billy. Do you have any question or remarks to the author?
Maybe I can ask how the transmission time is expressed in this model, or maybe it's not necessary.
The transmission time is basically, if I go back to the channel, is basically part of an internal clock of that channel model, which is only started when we are going into the transmitting state right here. We can reside into in this transmitting state until that clock reaches the delay value, basically, which refers to that worst case transfer delay. But then we have to leave that state again. At that point, these clocks are reset right here, and they don't advance in this idle state right here. And therefore, as soon as the next message is sent, well, it can be started again. Does that answer your question?
Yes, thank you.
Okay.
I would like to ask the similar questions. This is the delay. The delay is the constant for each of the actor in this model, because it could be something like the random value around some.
Basically, it's a worst case delay. So I don't know if you can see that that's a less or equal than. So basically, what that means is that we have that as a assumed upper bound for the transmission time, and everything else, basically, which is less than that, is done via model checking. So in the case that we have a shorter transmission time, that would be also feasible by that model. On the other hand, the worst case indeed occurs when that worst case transmission time is taken into account.
Okay. Thank you very much again.